There's a reason your smartphone works. It's not just silicon and software. It's helium, specifically liquid helium at 4 degrees above absolute zero. Without it, you can't manufacture the chips that power every piece of modern technology. And right now, after that Iranian missile strike on Qatar, we're running out of it. TSMC, Samsung, Intel, the companies that make every processor and every device you own, are facing a supply crisis with no solution because you can't substitute helium. You can't synthesize it. You can't mine it faster. And when the stockpiles run dry in 3 to 6 months, chip production doesn't slow down, it stops. The AI industry everyone thinks is unstoppable. It's collapsing because there aren't enough chips to train the models. Your next phone, it's not getting cheaper. It might not exist at all. This is the story of the invisible element holding civilization together and how one missile strike exposed that we've been living one supply disruption away from technological catastrophe. Let me explain the physics of why helium is absolutely irreplaceable in semiconductor manufacturing, because understanding this makes it clear why there's no workaround and no substitute. The problem isn't just that helium is useful or convenient. The problem is that the laws of physics make it uniquely necessary for specific critical processes. Semiconductor fabrication requires creating microscopic circuits on silicon wafers. We're talking about transistors measured in nanometers, billionths of a meter. At the most advanced manufacturing nodes, transistors are 7 nanometers wide. That's roughly the size of a few dozen atoms. Creating structures that small requires extraordinary precision in every step of the process. One critical step is plasma etching, where you use ionized gas to carve away specific layers of material on the wafer. This process generates enormous heat. We're talking thousands of degrees Celsius in localized areas. If you don't cool the wafer fast enough, thermal expansion causes defects. The circuits warp, the transistors fail. The chip is worthless. Here's where helium becomes essential. You need to cool wafers from thousands of degrees to near room temperature in seconds. The cooling has to be uniform across the entire surface. It has to happen without introducing any chemical contamination. And it has to maintain vacuum conditions because exposure to oxygen or water vapor at these temperatures would ruin everything. Liquid helium is the only substance that can do this job. It reaches temperatures around 4 Kelvin, 4 degrees above absolute zero, the coldest temperature physically possible. At those temperatures, helium remains liquid instead of freezing solid like every other element would. This liquid helium can absorb enormous amounts of heat very rapidly while maintaining stable temperatures. More importantly, helium is chemically inert. It doesn't react with anything. You can blast liquid helium across a silicon wafer covered in delicate circuit structures, and it won't oxidize the metal, won't contaminate the materials, won't introduce impurities that would affect electrical properties. It just absorbs heat and evaporates away, leaving nothing behind. No other substance has these properties. Liquid nitrogen gets cold 77 Kelvin, but that's not cold enough for the most advanced processes. Liquid hydrogen gets even colder and has better thermal properties, but it's chemically reactive and explosively flammable. You can't use it in a semiconductor fab without catastrophic safety risks. Liquid helium is the only option that combines the necessary temperature, thermal properties, chemical inertness, and safety profile. This isn't a case where engineers could redesign the process to work differently. The physics of creating nanometer-scale structures in silicon requires precise thermal management. The economics of semiconductor manufacturing requires high-volume production with minimal defects. Helium cooling is what makes both possible. Remove helium from the equation and you can't manufacture advanced chips at scale. Period. Now understand the scale of helium usage in the semiconductor industry. A single modern fab like TSMC's facility in Taiwan or Samsung's plant in South Korea uses thousands of liters of liquid helium per day. Multiply that across dozens of fabs worldwide, and you're talking about enormous helium consumption. The industry as a whole accounts for roughly 15% of global helium demand. Before the Qatar strike, that demand was barely being met. Global helium production was around 200 million cubic meters annually. Semiconductor demand was about 30 million cubic meters. The market was tight but functional. Now, with Qatar's 66 million cubic meters of annual production offline, the entire supply-demand balance has collapsed. Semiconductor manufacturers stockpile helium, but those reserves are finite. TSMC has maybe 4 months of full capacity operation before they need to start rationing. Samsung might have 5 months. Intel perhaps 6, depending on their contract terms and storage capacity. But all of them are operating on borrowed time. When the stockpiles deplete, production has to slow regardless of demand, and demand is at all-time highs. The AI boom is consuming chips faster than they can be manufactured. Companies like OpenAI, Google, Microsoft, Meta, they're all racing to train larger language models, which requires massive compute clusters with tens of thousands of advanced processors. Every data center expansion, every cloud computing build-out, every AI startup, they all need chips. NVIDIA can't produce GPUs fast enough. AMD is ramping production but still can't meet demand. The market for advanced semiconductors is supply constrained even before helium becomes an issue. Now layer the helium shortage on top of that. TSMC announces they're reducing production by 20% starting in 3 months due to helium constraints. Samsung follows with a 15% reduction. Intel delays bringing new fabs online because they can't secure helium supply contracts. Suddenly, chip supply that was already tight becomes catastrophically insufficient. What happens to prices? Basic economics: when supply drops and demand stays constant, prices spike. Chips that cost $200 now cost $300. High-end processors that were $500 become $800. And that's if you can get them at all, because major customers with long-term contracts get priority. Smaller companies, startups, research institutions, they get priced out entirely or face massive delays. The AI industry takes the biggest hit. Training a frontier language model like GPT-4 or Claude required thousands of GPUs running for months. The companies doing this, OpenAI, Anthropic, Google, Meta, had plans to train even larger models with even more compute. Those plans just became impossible. Not because they lack money or expertise, but because they literally cannot acquire the chips needed to build the training clusters. AI development doesn't just slow, it potentially stalls. The next generation of models that might have been released in 2027 or 2028 gets delayed indefinitely. Research progress that depends on scaling compute hits a wall. Startups that were betting on AI capabilities improving every year suddenly face a world where capabilities plateau, not because of algorithmic limits, but because of physical resource constraints. The broader economic implications cascade through every industry. Automotive manufacturers can't get the chips needed for electric vehicles and autonomous driving systems. Production lines sit idle waiting for components. Tesla, GM, Ford, BMW, they all face the same constraints. The transition to electric vehicles that governments worldwide are mandating and subsidizing suddenly hits a bottleneck, not because of battery supply or charging infrastructure, but because of chip shortages. Consumer electronics face similar problems. Apple, Samsung, Xiaomi, every phone manufacturer depends on advanced chips for processors, cameras, displays, communications. When chip supply tightens, phone production slows. That iPhone you were planning to upgrade to? Wait list measured in months if it's available at all. And when it is available, it costs $200 more than the previous generation, not because Apple is price gouging, but because their component costs jumped. Data centers that power cloud computing, streaming services, social media platforms, they all depend on continuous hardware refreshes with newer, more efficient chips. When those chips become scarce, expansion plans pause. New capacity can't be added. Existing infrastructure has to be maintained longer, running less efficiently, consuming more power. The digital economy that everyone takes for granted starts operating under constraints we haven't seen in decades. Medical technology gets squeezed. Modern medical devices, from diagnostic equipment to surgical robots to patient monitoring systems, all depend on advanced chips. When supply tightens, medical device manufacturers face the same allocation problems as everyone else. Production slows. Hospitals delay equipment purchases. Health systems in developing countries that were finally starting to access advanced medical technology suddenly can't afford the equipment or face impossible wait times. The defense and aerospace sectors become national security priorities. Military systems, satellites, communications equipment, missile guidance, radar systems, all chip intensive. Governments start intervening in chip allocation, demanding that defense contractors get priority access regardless of commercial demand. This creates political tensions between national security needs and economic requirements. Congress holds hearings. Senators demand answers. But there's no solution when the fundamental constraint is helium supply that can't be quickly increased. Research institutions face existential challenges. University labs conducting AI research, quantum computing development, materials science that depends on advanced simulations, all suddenly constrained by lack of access to compute. Graduate students can't complete thesis projects because they can't get GPU time. Breakthrough research that might have advanced human knowledge gets postponed because the physical infrastructure to conduct that research is unavailable. My sources tell me that within semiconductor companies, there's panic beneath the corporate messaging. Public statements talk about managing through supply constraints and prioritizing key customers. Internal discussions are about how to keep fabs operating when helium runs out, which product lines to shut down entirely, how to triage between customers in ways that minimize legal liability and reputational damage. TSMC executives are gaming out scenarios where they have to choose between producing chips for Apple or Nvidia or AMD. Samsung is planning which fabs to keep operating at reduced capacity and which to temporarily shut down. Intel is facing decisions about whether to prioritize their own product lines or their foundry customers. These are Sophie's choices with trillion-dollar implications. The geopolitical dimension adds another layer of complexity. The United States, facing domestic helium constraints despite having the Federal Helium Reserve, considers restricting exports to preserve supply for American semiconductor manufacturers and defense contractors. That protects U.S. industry but crashes Asian and European chip producers who depend on imported helium. China, which has been investing in domestic helium production and has some reserves, suddenly has a strategic advantage. Their semiconductor industry, already subsidized and prioritized, gets guaranteed helium allocation. Western companies face market-based scarcity while Chinese competitors have state-guaranteed supply. This shifts competitive dynamics in ways that accelerate China's progress towards semiconductor self-sufficiency. Taiwan becomes extraordinarily vulnerable. TSMC is the crown jewel of Taiwanese technology and a critical strategic asset. If TSMC can't operate at capacity due to helium shortages, Taiwan's economic and strategic position weakens. China could exploit this vulnerability, offering helium supply in exchange for political concessions. Or they could simply wait, knowing that if TSMC's production is constrained, alternatives in China become more viable. The semiconductor supply chain, already the most geopolitically sensitive industry in the world, becomes a flashpoint for great power competition. Who controls helium supply suddenly matters as much as who controls chip design or manufacturing capability. Resource nationalism over gas most people associate with party balloons becomes a central feature of 21st century strategic competition. This is what supply chain fragility looks like when pushed to breaking point. We built a global technology industry dependent on an element that comes from a handful of locations, is non-renewable, can't be synthesized, and has no substitutes. We concentrated helium production in politically unstable or strategically contested regions. We built just-in-time supply chains with minimal buffers, and we assumed nothing would disrupt this delicate balance. One missile strike proved that assumption catastrophically wrong. The Qatar helium facility going offline isn't like an oil refinery fire where production can be restored in weeks or alternative sources ramped up quickly. This is a 3 to 4 year disruption minimum, possibly longer if reconstruction faces technical challenges or additional strikes occur. The chip industry is about to experience what economists call demand destruction, not because people want fewer chips, but because supply constraints force people to make do with less. Phones get kept longer, computers don't get upgraded, AI models don't get trained, data centers don't expand. The technological progress we've taken for granted for decades slows not because innovation stops, but because the physical resources needed to build the innovations aren't available. This creates an opening for alternative approaches. Companies invest in chip recycling, extracting and reusing chips from old electronics rather than manufacturing new ones. Engineers redesign systems to use older, less advanced chips that require less helium to manufacture. Software gets optimized to run efficiently on existing hardware rather than assuming endless performance improvements. These adaptations happen, but they take years to implement fully and represent a step backward in capability compared to what would have been possible with unconstrained chip supply. The helium crisis is teaching us that modern technological civilization rests on surprisingly fragile foundations. We depend on complex supply chains spanning the globe, concentrated in a small number of critical locations for materials and elements that can't be easily replaced or quickly ramped up. When those supply chains break, the consequences cascade through every sector of the economy. Your phone not getting cheaper is a symptom. The AI industry stalling is a symptom. Data centers constrained, cars unaffordable, medical equipment unavailable, all symptoms of the same underlying problem. We build a technological civilization that requires continuous input of rare elements and materials, and we didn't build resilience into those supply chains because we assumed they'd always function. Iran's missile strike on Qatar didn't just destroy a helium facility, it exposed that assumption as dangerously wrong. And now we're living through the consequences of that exposure. chip production stopping, AI industry collapsing, technology progress constrained, not because we lack knowledge or capability, but because we lack helium. 4 Kelvin or civilization falters. That's the reality we're learning to live with, and there's no quick escape from it. Let me walk through the specific timeline of how this chip shortage will manifest in your daily life over the next 12 to 18 months, because understanding the cascade helps you see just how deep this crisis goes. We're not talking about inconvenience. We're talking about fundamental changes to how technology functions in society. In the immediate term, the next 3 months, you won't notice much difference. Chip inventory in the supply chain buffers the shortage. Phones are still available. Computers are still shipping. Data centers are operating normally. The only visible sign is price increases for high-end products as manufacturers pass along their higher component costs. A flagship phone that was $1,200 is now $1,350. An advanced GPU that was $800 is now $1,000. Annoying but not catastrophic. Months 4 to 6 is when availability problems start. You walk into a store to buy a new phone and the model you want isn't in stock. The salesperson tells you it's on back order, maybe 3 weeks. You check online and find that shipping estimates have doubled. Reviews start mentioning that certain products are hard to find or selling out quickly. Tech news sites run articles about supply constraints, but most people still think it's temporary. The AI companies are the first to really feel the pain. Training runs that were scheduled for summer 2026 get postponed because the GPU clusters can't be built. OpenAI planned to train GPT-5 on 50,000 H100 chips. They can only secure 30,000. That's not enough for their planned model architecture. They either train a smaller model or delay until more chips become available. Neither option is what they wanted. Anthropic faces the same problem. Claude's next generation was supposed to use a massive training cluster. The chips aren't available. Google's Gemini team, Meta's Llama research, every AI lab worldwide hits the same wall simultaneously. The compute that was supposed to enable the next leap in AI capabilities simply doesn't exist because the chips can't be manufactured at the scale required. This creates a strange paradox. AI was supposed to be the unstoppable force reshaping every industry. Every company was scrambling to integrate AI, to build AI products, to hire AI researchers. And suddenly that's all constrained not by algorithmic limits or data availability, but by physical chip supply. The AI revolution that everyone thought was inevitable just hit a speed bump that might last for years. By months 6 to 9, the consumer impact becomes undeniable. Your phone is now 2 years old and starting to slow down. You want to upgrade. You check Apple's website and the iPhone 17 is back ordered until next quarter. You check Samsung, same story. You check Xiaomi, Oppo, every manufacturer, they're all facing the same supply constraints. The era of annual phone upgrades is over, not because consumers lost interest, but because the products literally cannot be manufactured in sufficient quantities. Laptop and desktop computers face similar constraints. That gaming PC you were planning to build, the GPU you need is either unavailable or priced 3 times higher than it should be. The thin and light laptop for college? Waitlist is 4 months. High-end workstations for professionals? Companies are rationing allocation to their most important business customers, which means individual consumers simply cannot buy them. The automotive industry enters full crisis mode. Modern cars are computers on wheels. A single vehicle contains hundreds of chips managing everything from engine efficiency to safety systems to infotainment. When chip supply drops, car production has to drop proportionally. Ford announces they're cutting production 25% for the next 6 months. GM follows with similar numbers. Tesla, which was supposed to be ramping Model Y production, has to scale back plans. Dealership lots that were finally starting to fill up after previous chip shortages empty out again. This creates weird secondary effects. Used car prices spike because people can't buy new vehicles. Cars that would normally depreciate start holding their value or even appreciating because supply of replacements is constrained. Repair shops get overwhelmed because people are keeping older vehicles running longer. The entire automotive market distorts around the chip shortage. By months 9 to 12, we're in genuinely different technological territory. Companies that depended on continuous tech upgrades to stay competitive can't upgrade. Data centers running on 5-year-old servers that should have been replaced are limping along because newer servers aren't available. This means slower cloud services, less efficient data processing, higher energy costs for the same computational work. The startup ecosystem takes a major hit. If you're building a company that requires significant compute, AI startups, biotech doing simulations, financial firms running quantitative models, You're at a massive disadvantage compared to established companies that already have infrastructure. The big players with existing server farms can keep operating. Small players trying to enter the market can't get the hardware needed to compete. This entrenches incumbents and kills innovation at exactly the moment when AI and other compute-intensive technologies were supposed to be creating opportunities for disruption. Education and research institutions face impossible choices. Universities that were expanding their AI research programs can't get the GPUs needed for student projects and faculty research. National labs conducting scientific simulations face compute constraints that delay research. The next generation of engineers and researchers trains on inadequate equipment, which sets back their capability development. This has compounding effects over years as the people who would have driven technological progress forward lack the tools to develop their skills fully. Healthcare technology hits critical shortages around the same time. Advanced medical imaging, genomic sequencing, drug discovery simulations, all chip intensive. When chips become scarce, medical device manufacturers can't maintain production. Hospitals face longer wait times for diagnostic equipment. Research institutions working on new treatments and drugs slow their work. Lives are lost not because medical knowledge is inadequate, but because the computational tools needed to apply that knowledge aren't available. The developing world gets hit hardest. Wealthy countries and major corporations use their resources to secure what chip supply exists, even at elevated prices. Poor countries and small organizations get completely priced out. Hospitals in Africa that were finally starting to access modern diagnostic equipment suddenly lose access. Universities in Southeast Asia that were building research programs face technology deficits. The digital divide that was slowly closing rips open wider than before. By months 12 to 18, we're operating in a fundamentally different technological regime. The assumption of continuous improvement, Moore's Law, annual upgrades, expanding capabilities is dead for the foreseeable future. People make do with existing technology. Software gets optimized to run on older hardware. Engineers design systems to use less compute rather than assuming compute is abundant. This is an apocalyptic collapse. Society continues functioning, but the trajectory changes. Instead of exponential technological progress, we get stagnation or marginal improvements. Instead of abundant compute enabling new capabilities, we get scarcity forcing compromises. Instead of everyone benefiting from improving technology, we get inequality as the wealthy and powerful secure scarce resources while everyone else makes do with less. The economic analysis shows this clearly. Global GDP growth estimates get revised downward because technological progress is a major driver of productivity improvements. If technology can't advance at the expected pace, productivity can't grow as fast, which means GDP grows more slowly, which means lower living standards than would otherwise be possible. We're talking about trillions of dollars in economic output that won't be created over the next 5 years because of chip constraints driven by helium shortage. Stock markets react as this becomes undeniable. Technology stocks, which were the best performers for 2 decades, face a new reality where growth is constrained by physical resource availability rather than just demand and innovation. Valuations that assume continuous expansion adjust downward. Retirement accounts built on tech stocks lose value. The wealth effects ripple through the economy as people feel poorer and spend less. The workforce implications are significant. Software engineers and data scientists who are in high demand face a different market. If AI development stalls due to lack of compute, demand for AI researchers decreases. If data centers can't expand, demand for cloud infrastructure experts flattens. If consumer electronics production slows, demand for hardware designers declines. The skills that were supposed to be the future face constrained demand because the industries employing those skills are constrained by chip supply. This creates a fascinating prisoner's dilemma in the semiconductor industry. Every company knows that helium shortages will constrain production. Every company knows that increasing capacity now while helium is available would give them competitive advantage later. But building new fabs takes years and costs tens of billions of dollars. Do you make that investment knowing helium might not be available to operate the facility when it's complete? Or do you hold off and risk falling behind competitors who do build capacity? My sources tell me the major players are taking different approaches. TSMC is betting on helium supply, recovering and building additional capacity in Arizona and Germany. Samsung is being more cautious, focusing on efficiency improvements at existing facilities rather than major expansion. Intel is hedging, building some new capacity, while also investing heavily in helium recycling technology that could reduce their dependence on external supply. Each strategy has risks, and the outcome won't be clear for years. The recycling angle is particularly interesting. Current semiconductor fabs vent helium after use. It escapes into the atmosphere and is lost forever, but it's technically possible to capture that helium, reliquefy it, and reuse it. The equipment to do this is expensive. We're talking hundreds of millions of dollars per facility, but it can recover 80 to 90% of helium used. If helium prices stay elevated, that investment becomes economical. Major fabs are scrambling to install recycling systems, but the equipment has long lead times and there aren't enough suppliers to meet sudden demand. This is another area where concentration of expertise creates bottlenecks. Only a handful of companies worldwide manufacture the specialized cryogenic equipment needed for helium recycling. They're booked, Saul,